About the Latch phenomenon, and we have to think about the CMOS. And technology. Okay, CMOS is combination of a P channel and N channel MOS, something like this. And if you make a connection of PMOS and CMOS, then we can have an advantage like a standby current, minimize the standby current is almost zero, and low impedance for switching. And say these two are very important, and it can include large noise margins and wide operation supply range. Can you cover this part with the lens? Okay. So let me draw. Where is it? Oh, we don't have a white chalk. Typical CMOS structures. Let's see. We have PMOS, P plus, and then we can have, I have to draw this to the scale. We are going to have field outside, then, let me do the whole thing again. I need more space here. Let's see. Let me draw a little bit. And then I'm going to have a field outside, which is much higher than this. If you have N substrate, then this is going to be the P plus, and the PMOS, and then you're going to have P well, and then set it, almost something like this, okay? And then we send a little bit more. Here we're going to have a P plus, and here we're going to have N plus. Okay, and then we set this to a VDD, and then we get a connection of this two for we assess our ground. Right. And then this is the field oxide. So actually what you can have here is this is going to be connected to this gate for and this part is going to be connected to this part. Oh, okay, something like this. This is you can do the same thing with the opposite type of MOS. In other words, if you have a P substrate, then this thing is going to be M plus, and this thing is going to be P plus, PMOS, and then we have to set up the N well. You can have exactly the same situation. Okay. This is a typical example of the CMOS inverter. Okay. CMOS inverter. Well, there are two types of CMOS. One is based on the PMOS, and you set up the P well to have MMOS. That is the base. This is the case where the PMOS is the base. But if you set up the NMOS as a base, then you can construct exactly the same structures to get a CMOS. But these days, this is preferable. Because most of the memory devices is constructed on the base of NMOS. So if you use this type of CMOS, then all you have to do is use exactly the same procedure for the NMOS, and then you just use an extra mask for the N well, and then construct the PMOS on the necessary positions. And so you can adopt the MMOS based CMOS rather than the PMOS based CMOS. But in this lecture, we just have to go for the type that is shown on the board. And so let me just let me try to explain the latch phenomenon on this circuits. Okay, and most of the theories has been I just got from the doctor in the Stanford University. That's the right thesis, PhD thesis in Stanford. 1980. Okay. And if you look at this cross section of the CMOS, now you can see that we can identify a bipolar structures, okay, coming from here, and then if you like this, maybe the base of the one bipolar transistors, and we call this P plus N minus and P well bipolar, okay, and then you can set at the same time this thing can be connected to the bipolar transistors, which is going to be constructed from here and here, something like this, okay? And then this may connect it to this base here, okay? So we have, we're going to have, and this one is N plus P well and N minus substrate bipolar transistors, and this is a vertical transistors bipolar, and then this is a lateral bipolar transistor. So we can think something like this, okay? It just have been constructed on the same silicon or wafer in the two-dimensional silicon surface, so that if there is a way for the electrons and the holes to get a path, then those free carriers can see the bipolar structures, one lateral bipolar structures and one vertical bipolar structures, and then if these two bipolar structures, if they can have some current on the base, then the bipolar transistor is going to be triggered on. Okay, if this bipolar transistor is on, then we are going to have a tremendous current passing through this drain and the source. Okay, through these two bipolar transistors, and enormous amount of current can pass when this bipolar transistor is on, triggered on, and that high current will hit the whole thing. So the latch up process itself is not going to ruin the device, but the resultant heat will going to destroy the circuit. So the current induced heating is the problem. We have to prevent somehow this triggering process. And if you look into the circuit of this, then you may see that the VDD and you can have bipolar transistors, something like this, and then there's Rn, and that is grounded, and you can see grounded, and here see this RP, and that is connected to this 3DD. Okay? And according to that, the figure, this is a P and P, and let's say this is a P plus, and there is N sub, and this is a P well, okay? And this bipolar, vertical bipolar transistors is a N plus, and then a P well, N sub. So here the RP, we have new things as RP and RN, and RP is the resistance of bulk substrate away from N plus 3D contact, which means that R sub P is resistance coming from the contact, 3D contact here, okay? And then Rn is resistance of P well over to P plus contact. So that is here coming from this direction, that is Rn. So if Rp and Rn is crucial, if they are zero, then VBE, emitter base voltage, can never get to 0.7 volts, which is necessary. That is the threshold voltage for the MOS transistors, threshold voltage for MOS, okay? Needed to turn NPN and PNP on. So if we can minimize this RP and RN, these bipolar transistors is not going to be turned on, so that we are not going to have any Latch process. And as you can see here, the lateral transistor P plus N P fairly wide base, so that the beta is very low in this case, right? And N plus Pn, the vertical bipolar transistors, is fairly high beta due to short base. So for latch up to occur, one of the bipolar and there's three ways for these two, one of these bipolar transistors to be turned on, and number one is the overall voltage of VDD, and that is if you have here the P plus and P plus, and then you have a well here, P well, and then if you have over voltage, this avalanche breakdown occurs at the source, so that the hole may be injected to P-well to trigger vertical bipolar transistor on. So the over voltage of a VDD may cause the latch up by turn on the vertical bipolar transistors. Okay. And number two is voltage transient. If you change the switching, for example, transient or VDD may widen the depletion layer of P1. In other words, if you have a transient of this VDD lines, then this electric field is going to contact with a P-well here and substrate, so that the in this P-well, the space charge regions can be modulated by these voltages coming from this N plus VDD. Okay, this potential may affect the bipolar transistors and the vertical bipolar transistors, so that IR drop occurs, which can forward bias the junction. And lastly, we can think of input protection overdrive. And this means if you have a P plus here, P plus and P plus in this drawing, and then we have P well, and we have M plus and M plus, and as you can see, we have a P plus and N sub diode here, and then we have N plus P diode. We have two diodes here, right? So if we have a if the input exceed VDD, then P plus N diode will inject volts. Okay, and then this thing is going to be collected to the P well, and then NPN base current. It works as it's going to be NPN bipolar base current, so that the NPN bipolar is going to be turned on through this. And it has been studied by the actually in Stanford University for in his PhD thesis for Latch to occur. He found that the loop gain. The loop gain means the circuits corresponding to the latch up that we have discussed, which is again VDD. And then this circuit is just Rn, and this is Rp. This loop, okay? In this loop, the gain NPN should be greater than IDD beta PNP plus RP and IDD plus 1 over beta P. Okay, this is the equation that he found in its study. And there are typical numbers in the nodes where, let me just write it down for you. And NP and PNP. PNP is 00110 and RP 25 ohm to 500 ohm and RN is 25 ohm to 10 kilo ohm. So if you add, insert these numbers to this equation, you can see that the gain of NPN, the vertical transistor, bipolar transistor, is easily, this equation can be satisfied, which means the normal CMOS devices is very weak, okay, for the latch up. Latch up most probably can occur in the normal CMOS device. So we have to have a CMOS to have those advantages that I mentioned early in this lecture, but it is very immune to the latch up process, which is going to kill the device by the heat. We have to find a way to prevent this latch up process, otherwise we cannot use this CMOS process. All right? And scaling down, scaling means miniaturization of the device. Scaling down, then we have to have a short base, and in the bipolar transistors, for example, the distance between these two is going to be shortened if you scale down the whole thing to enhance the integration level. Then this means we have a beta goes up, and so this scaling is going to make the device more vulnerable to the latch out process. So we have to find a way to prevent the latch out. We have more problems related to latch out. So from now on, let me just discuss something about how we can prevent the latch out. One thing, we can change the layout. Lay out the structures to minimize Rn and Rp, okay, by putting lots of VDD. Connections, and we can minimize P plus to P well spacing. I'm sorry, maximize. In this case, we have to maximize the P plus PL spacing so that we have a very big base region for this PMP bipolar transistors to make beta down. The gain is going to be decreased. Okay? And also we can have a backside contact. To minimize RP. So we can solve this problem to a certain level by changing the layout. That is one way. And also we can set new structures. We can add new structures like channel stop implants. Channel stop implants means on this field oxide, below this field oxide, we have a implantation to make a M plus, that is going to be N plus implants. And this is called the channel stop. Okay? And if you have a M plus, then the M plus channel stops implants may reduce RP and RN and increase PNP base width, so that we can prevent the Latch process. And we can also have a pseudo collectors. This pseudo collectors is going to be a P plus ring around the device, such that we're going to build a P plus ring on this device, something like this. Okay, that is a P plus. We set up a new P plus ring. And this P plus is going to, the P plus ring will collect injected holes thereby. This injected holes is coming from the VDD contact in the M plus, which is going to work as a base current, okay, base current, to trigger NPN bipolar, okay, thereby preventing collection by PWL. So it just can see that this bipolar, you have an extra collector. You're going to build the extra collectors right here. This is the VDD and this RP. Okay. And this connections. And number 4, is set a emitter resistance. Set the emitter resistance means in terms of the circuit, now what you are going to do is you're going to set a new resistance for the emitters of this bipolar transistors, lateral bipolar transistors, as well as the vertical bipolar transistors here. Now you are going to have new R's of En, this new resistance. Okay. Besides this Rn and Rp. Okay. So this new register, say, can be put on the device something like, now what you're trying to do is you're going to set a polysilicon with a high resistance, and then that polysilicon high resistance material is going to surround this VDD N plus here to make a new REP. Okay, and then also you can have polysilicon ring on this P plus to make R so En. Okay, and then the avalanche electron hole creation, which is going to use for the base current on this bipolar transistors, is going to be reduced with this emitter resistance. So this emitter degeneration decrease effective beta of bipolar devices. And lastly, we can think the lifetime control by what should I say, contaminating, okay? Introduce damage, deep level traps, and that is platinum and gold things. We just implant those things in the device. Then carrier lifetime will decrease, so that NPN and PNP beta is going to be decreased, so that we can have reduce the chance for latch up for the device. One more thing that we can apply to reduce the latch up, and that is the epitextual buried layer. Buried layer. Well, in theory it is possible, but it never been exercised in the actual process because the complexity of the process. And this is just like the bipolar transistors. When you set up the PMOS, a CMOS, by making this two, basically what you are doing is you use the N sub, and then you grow the epitextual layer. And then you have P well, and then it is going to be punched into this N substrate by out diffusion of this dopant, so that you have a P here and works as a buried layer. Okay, then the also P and the also N is going to be minimized by using moderately doped, which is 10 to the 17th and 10 to the 18th per cube substrate. And P buried layer. RP and RN can be reduced. Okay. So we just overview the latch up process in the CMOS, which is inevitable and becomes serious as we scale down the device. And we can, I just introduced the 6 ways to minimize the latch up process. You cannot totally eliminate the latch up, but you can reduce the chance to get the latch up in your device by and those 6 methods all cost the integration levels and complexity of the process, but it seems that this cost is inevitable. We have to pay this cost to prevent the latch up. Because once you have a latch up in your device, then everything is bound down. So we cannot use that device anymore. So it is very important to have to prevent, to minimize the latch up thing in CMOS process. Okay. The next week on Monday, we are going to discuss about the geometry effect on the MOS devices as a final topic for the MOS. And on Wednesday, we begin to discussion about the bipolar transistors. Okay? Have a nice weekend.